Hi everyone, welcome to this tutorial on large language model enhanced recommender systems. My name is Zijian Zhang. Today, we will dive into a cutting-edge and dynamic research area, how to leverage large language models to enhance recommender systems. This tutorial is a collaborative effort by researchers from Xi'an Jiaotong University and City University of Hong Kong. This tutorial will systematically investigate the most up-to-date works of LLM-enhanced recommender systems to boost this direction. We will explore the foundational concepts, dive into the motivations behind integrating LLMs with recommender systems, and outline the innovative ways these two powerful technologies are converging. Here is a quick overview of our presentation agenda. We will first deliver the Section 1 introduction, setting the stage by discussing the background of recommender systems, their limitations, and the motivation of LLM-enhanced recommender system. Section 2 by Pengyue Jia will focus on knowledge enhancement. We will explore how LLMs infuse external knowledge into RIs, primarily by deriving rich textual descriptions for users or items. Section 3 by Ziwei Liu will then cover interaction enhancement. This section details how LLMs address data sparsity by generating new user-item interactions, which are then used to augment the training data. Sections 4.1 by Maolin Wang and 4.2 by Yuhao Wang are dedicated to model enhancement. This is where LLMs directly assist or influence the recommendation model itself. We will explore subcategories like model initialization, model distillation, embedding utilization, and embedding guidance. Finally, Section 5 by Yejing Wang will present our conclusion, summarizing the key findings and discussing promising future directions for the LLM-ERS field. To understand the need for LLM-enhanced recommender systems, we first need to review the position of recommender systems. With the growing information overload, the content servers are required to solve a pressing issue that how to provide users with more accurate and efficient personalized recommendations. This funnel image on the left perfectly illustrates this challenge. Given a massive amount of information on the web, only a tiny fraction is actually relevant to any single user. This is where recommender systems step in. They act as intelligent filters to help users discover items they might like. This foundational role makes recommender systems critical for the success of many online platforms. Basically, recommender systems consist of two components: user interaction data like bottom right. It includes user item interaction records and some metadata of users and items, like user profile and item attributes. The top right part recommendation model is trained on interaction data to approximate users' historical interaction, capture user preference, and infer which new item the user may prefer. While recommender systems have widely proven the efficacy of precisely understanding users' preference and yield enormous benefits for content server, traditional recommender systems rely heavily on historical user-item interactions and handcrafted features, yet face serious limitations. We identified the primary limitations into three aspects. First, at the feature level, features are often converted to numerical or categorical values for utilization, but they lack reasoning and understanding from the knowledge aspect. This leads to a lack of reasoning and knowledge in feature representations. They struggle to capture deeper semantic meanings or word knowledge associated with items or users. Second, at the interaction level, data sparsity leads to insufficient training for recommender system models. This cold start problem or long-tail distribution severely hinders the model's ability to make accurate recommendations, especially for new users or items. Finally, at the model level, recommendation models according to an embedding and deep network pattern can only capture collaborative signals, while ignoring semantic information. This limits their ability to generalize beyond observed interactions and provide explainable recommendations. Now, let's turn our attention to how large language models offer solutions to these challenges. The fundamental strength of LLM is the superior reasoning and comprehension abilities. It has extensive word knowledge and can intelligently understand and process natural language. This directly compensates for the shortcomings we just discussed. At the feature level, the LLM utilizes reasoning abilities and word knowledge to derive textual descriptions for users or items. These descriptions serve as extra features to supplement reasoning and understanding knowledge. At the interaction level, to face the data sparsity issue, some research studies adopt the LLM to derive new user-item interactions. At the model level, the LLM can analyze the interactions from a semantic view, assisting the conventional recommender models. This leads us to the concept of LLM-enhanced RS. In this tutorial, we discuss the LLM-enhanced recommender system, abbreviated as LLM-ERS. It means the conventional recommender systems are enhanced by LLM via assistance in training or supplementary for data, while no need for LLM inference during the service. Existing tutorials and surveys mainly focus on how to use the LLM itself as a better RS, including generative recommendation and discriminative recommendation. By contrast, we only discuss LLM enhanced recommender system in this tutorial, which has been rarely introduced. This pushes the LLM into the online system with a large step by eliminating the utilization of LLM during inference. This design choice is vital for maintaining the low latency required for real-world recommender systems, making LLM-enhanced RS a highly practical and efficient approach. As depicted in the figure, we categorize these enhancements into three main lines based on the component of an RS model: knowledge enhancement, interaction enhancement, and model enhancement. Knowledge enhancement utilizes reasoning abilities and word knowledge of the LLM to derive textual descriptions for users or items. These descriptions will serve as extra features to supplement reasoning and understanding knowledge, and thus they can tackle the feature-level limitations of traditional recommender systems. To solve the data sparsity issue, the interaction enhancement methods adopt the LLM to derive new user-item interactions. The LLM can analyze the interactions from a semantic view, so some model enhancement works have tried to make use of the LLM to assist the conventional recommender systems addressing the model-level limitation. Our first main category of LLM enhancement is knowledge enhancement, aiming to augment RS on the feature level. The core idea here is to leverage LLM's extensive word knowledge and powerful reasoning abilities to explicitly enrich features of users or items. In this category, LLM-ERS often utilize explicit knowledge to augment the recommender system. On the left, we have summary text augmentation. Here, the LLM is prompted with existing user or item textual interactions. For example, given a user who has viewed something he or she is interested in, the LLM then generates a summary text, like he or she likes something, which captures the user's preferences or item characteristics. This summary text is then often encoded by a general language model, such as BERT, and used as an extra feature for the RS model. On the right, we have knowledge graph augmentation. Instead of unstructured text, LLMs can be used to generate a knowledge graph or augment an existing knowledge graph for enhancing traditional RS. An LLM can be prompted with an item's name to ask, given an item named something, does it have the attribute? And the LLM then helps to build or complete a knowledge graph. This structured knowledge encoded by a knowledge graph encoder also serves as supplementary features for the RS model. Both methods aim to supplement reasoning and understanding knowledge for features, directly addressing limitation 1. Since these enhanced features can be derived and saved in advance, the demand for LLM will avoid during the service, leading to efficient inference. Our second category, interaction enhancement, is designed to tackle the critical issues of data sparsity in traditional recommender systems. The idea is straightforward. Using LLMs to generate new synthetic user item interactions, effectively augmenting the training data. This augmentation only occurs during training, so it introduces no additional inference burden during service. As illustrated in the diagram, we categorize these approaches based on the type of output the LLM provides, text-based and score-based. On the left, we have text-based interaction enhancement. Here, the LLM is prompted to directly augment by recommending an item name, like item 2. For instance, given a user who has viewed something and a candidate side item 1, item 2, and so on, the LLM might be asked to choose from them. The generated item name is then added to the dataset as an augmented interaction. On the right, we explore score-based interaction enhancement. To mitigate the out-of-corpus problem and difficulty of selecting from a large item set, these methods leverage the LLM to derive the logits or probabilities of possible interactions for a set of candidate items. As shown, the LLM output scores 0.02, 0.31, 0.05 for different items, and augmented items are generated by ranking. Both text-based and score-based methods serve the same purpose, to increase the interaction data for training, making the recommender systems more robust, especially in sparse data environments. Our final major category is the model enhancement. This line of work directly injects the powerful abilities and semantics of LLMs into traditional recommendation models. The goal here is to address challenge 3, where traditional models often overlook semantic understanding. This slide illustrates the first and second key subcategories of model enhancement. On the left, we have model initialization. This approach leverages LLMs to pre-train or initialize the weights of the RS model before the main training process. Just as pre-trained weights can help model convergence and preserve learned information in other fields, LLMs can inject rich semantic knowledge to the RS model's parameters. Some approaches apply pre-trained weights to the whole RS model, while others are for the embedding layer. On the right, we explore model distillation. This technique, inspired by knowledge distillation, involves transferring the knowledge from a large, powerful LLM, that is the teacher, to a smaller, more efficient RS model, that is the student. Despite the gap between discriminative RS models and generative LLM, existing studies design feature-based and response-based distillation ways to address such an issue. Both model initialization and model distillation only need the LLM to assist in training RS models, ensuring that LLM usage is eliminated during serving, thus meeting the latency requirements of real-time service. Continuing with model enhancement, this slide presents the third and fourth subcategories. On the left, we have embedding utilization. In this approach, embeddings derived from LLM, such as the hidden states of the last transformer layer of the LLM, are directly utilized to enhance traditional RS as a semantic supplement. The diagram shows the LLM outputting embeddings which are then fed into the RS model. This line of work can be categorized into user-only, item-only, and user-item based on the aspect LLM embeddings address in the traditional RS. On the right, we dive into embedding guidance. This approach differs from direct embedding utilization, as it uses the LLM embeddings only as the guidance for training or parameter synthesis. The diagram shows LLM embeddings influencing the RS model through a guidance loss, denoted as L-guide. This is particularly useful for user-only or user and atom scenarios. These methods collectively demonstrate the versatility of LLMs in enhancing different aspects of the recommendation model, moving beyond just data level improvements. All these techniques are crucial for building efficient and powerful LLM enhanced recommender systems that can truly understand and fulfill our user needs.
Hi everyone, I'm Jia from City University Hong Kong, and I will give the introduction to the knowledge enhancement part. So let me start by introducing the concept of knowledge enhancement in large language model enhanced recommender systems. Traditional recommender systems mostly rely on user-item interaction data. However, they often lack external knowledge that is essential for reasoning and understanding user preferences. And large language models or LLMs can fill this gap by injecting word knowledge and reasoning capabilities into the RS pipeline. As shown in the figure, the LLM can generate textual summaries, such as he or she likes, based on user browsing history, and these summaries are then encoded via a text encoder and fed into the RS model. On the item side, the large language model can also answer structured prompts like, does an item have a certain attribute, supporting knowledge graph construction and enrichment. This structured information is encoded through a KG encoder. And based on the form of knowledge used, we categorize the enhancement into three types: the summary text, knowledge graph, and their combination. This categorization allows us to systematically understand how different kinds of external knowledge can be utilized to improve recommendation quality and explainability. And we first focus on the summary text subcategory of knowledge enhancement. And this idea here is to leverage large language models to generate natural language summaries that describe either user preferences or item characteristics. And these summaries serve as additional semantic features for traditional recommender systems, improving both the reasoning and the personalization. Okay, and the LLM will return like a concise textual summary such as a user likes romantic comedy featuring strong female leads, and this output encodes rich semantic information that would be difficult to infer from interaction data alone. The generated text is then passed through a text encoder to convert it into a dense representation, which are compatible with the recommendation model's input space. And this strategy allows us to enrich traditional RS the models without modifying their architecture or relying on fine-tuning the LLM. And we further summarize the summary text enhancement into three types: the user-only, such as inferring multi-faceted preferences from browsing behavior, and item-only, such as generating detailed product or category description, and user and item, this combination. So the first paper is Lang. It's in the user-only subcategory, and the background is the explainability of recommendation systems is crucial for enhancing user trust and satisfaction. And the motivation is that fine-tuning LLM models for recommendation tasks incurs high computational costs and alignment issues with existing systems, limiting like the application potential of proven proprietary or closed source LLM models such as GPT-4. And the key components here are semantic embedding, user multi-preference extraction using zero-shot prompting, and semantic alignment. So first is about semantic embedding. In this step, authors use a text encoder to transform all item titles and user behavior sequences into semantic vectors, rather than using the simple ID embeddings. This semantic representation enables downstream modules and LLMs to better utilize the natural language understanding, where M is the embedding matrix of all item titles. And second is integrated model module. Lane can plug into mainstream sequential recommenders like susrec or BERT for rec, but replaces their ID-based embeddings with semantic text effectors. And it can preserve the model structure and ensure better interpretability. In this step, authors adapt a standard sequential recommender to use the semantic embeddings. For user, their history factors are combined with positional encodings to form the model input EU, which then produces sequential features QU. By using the meaningful semantic inputs, authors make downstream reasoning and explanations more interpretable while keeping the original recommender structure. And for extracting multi-preferences using LLM zero-shot prompts, here the authors use a zero-shot prompt with the LLM to summarize the user's multiple preferences from their history. The large language model generates a list of textual preferences, which are then encoded as semantic factors (PU). This approach leverages the LLM's understanding without any model tuning, providing diverse and user-specific features for later alignment. And for the next module, semantic alignment via multi-head attention, this module uses multi-head attention to align the user's sequential features QU with the LLM-generated preference factors PU. The formulas show the attention and feed-forward steps, and with normalization and residue to stabilize learning. And the result is a user representation that both effective for ranking and interpretable through the extracted preferences. And from the prediction for each timestamp t, authors take the user's aligned feature factor FUT and the embedding of candidate item MI and compute the product. This operation measures the semantic similarity between the user's current preferences and each possible item in the shared semantic space defined by text encoder. And this slide shows that Lang improves the NDCG at 10 and HR at 10 across all datasets and base models. For example, on SUSREP, Lang boosts performance by over 24% on beauty. And the key takeaway is that Lang enables plug-and-play integration of powerful LLMs for explainable the recommendation in real-world systems, providing enhanced performance and user-friendly explanations without any need for LLM fine-tuning. And next, we introduce the item-only method, GPU-org news. The background is that the explainability and informativeness of news metadata, especially category information, play a crucial role in personalized news recommendation. And for motivation, manually creating the detailed descriptions for news category is labor intensive, and existing category templates are too generic and providing sufficient semantic guidance. Pre-trained language models often fail to interpret short category names effectively without richer context. The contribution, the first is the generating the descriptions with LLMs and then incorporating descriptions into recommendation models. And to enrich the semantic meaning of categories, the authors use GPT-4 to automatically generate descriptions. The prompt is simple and fixed, and it returns clear text about what a category typically includes. These descriptions are longer and more informative than short category labels, and they require no additional tuning. After generating the category description, the next step is to feed it into the model. So the title and the description are concatenated using the token, just like standard BERT input formatting. And this augmented input is then encoded and used in downstream recommendation models. improving the system's understanding of both the topic and context. As we can see in the table, this method consistently outperforms both title-only and title plus the template-based baselines across all the tested models, like the NAML and NRMS and NPA, when using either the DistillBERT or BERT as the pre-trained language model. For example, in the NAML setting with DistillBERT, using the LLM generated descriptions improves AUC from 0.675 to 0.713 and NDCG at 10 from the 0.384 to 0.425, representing up to a 5.8% gain in AUC. And the takeaway here is the LLM generated category descriptions over a simple, generalizable, and training-free way to enhance item-side representations, which can be applied across architectures without additional domain-specific tuning. This makes GPT-org News both effective and highly practicable for real-world deployment. And for the user and item combination, we introduce KAR. So KAR is designed to break the boundary of closed word recommenders by introducing external knowledge from large language models. Existing recommender systems work only on in-domain behavior data, missing valuable common sense or reasoning capabilities. However, using LLMs directly as recommender is neither accurate nor efficient. So KR solves this by extracting two kinds of knowledge, the reasoning about user preferences and factual item information, and encoding them into compact factors that classical recommender can use directly. And it is model agnostic, explainable, and supports fast inference. So the first stage named knowledge reasoning and generation. This stage is responsible for acquiring the open world knowledge from LLMs. Since LLMs struggle with complex composite tasks, we use factorization prompting to break down reasoning into specific factors like gene, the theme, or director. And two prompts are designed, one for analyzing the user's historical behavior and preferences, and another for generating descriptive knowledge about candidate items. The outputs are plain text summaries, KIP and KIL, which will later be encoded. And these prompts guide LLMs to produce consistent and rich information aligned with recommendation needs. So after we get the text outputs from LLMs, we need to convert them into a form usable by CTR models. And this is done in two steps. First, a knowledge encoder converts each piece of textual knowledge into a dense vector via average pooling or CLS token. And second, a hybrid expert adapter transforms these vectors into the recommendation space. It uses a mixture of experts structure with shared and dedicated experts to capture both general and specific semantics. The final user and item knowledge factors are then added as new input fields into the CTR model. During training, these components are optimized jointly with the backbone, enabling the model to combine open world knowledge with traditional interaction signals. And this table shows the improvement brought by KR across 9 standard CTR models, whether the base model is a DFM or the int or DIN. The addition of reasoning and factual factors leads to consistent and statistically significant gains. And importantly, this is achieved without redesigning the model structure. And the open world knowledge is pre-computed and stored, so inference time remains fast. Overall, KR provides a general solution for bridging LLMs and recommender systems in a scalable and effective way. And for another work is Sling. So sequential recommendation captures users' dynamic interests, but traditional models rely on limited user item interactions and struggle with exposure bias. Large language models offer strong reasoning ability and open world knowledge, yet applying them directly is costly and often produces irrelevant results with one-step prompting. To tackle these issues, this paper proposes SLIM, a step-by-step knowledge distillation framework. It uses train of thought prompting on a large teacher model to generate recommendation rationales, which are then distilled into a small student model like Llama 2 7B. SLIM enables the student model to reason step by step with only 4% of the teacher's size. It supports both ID-based and ID agnostic recommendation and performs competitively with much lower cost. And this slide describes how the SLIM framework uses a large teacher, the LLM, to perform step-by-step recommendation reasoning using train of thought, the prompts. The teacher model outputs a rationale consisting of a user preferences, preferred brands or categories, and recommended items. And these rationales are then used to fine-tune a much smaller student model. The authors adopt a simplified prompting template, TS, and apply standard language modeling laws as shown in the equation to supervise the student model. The student, after training, can generate similar reasoning steps, enabling lightweight deployment. And this slide presents how SLIM applies the reasoning knowledge from the student model to the recommendation process. The student generates natural language rationales, RU, which are encoded using a text encoder like BERT in the first equation. And here FI is the item's description, such as title, brand, or a category. And this yields a user side and item side embedding in the same semantic space. So, and then I will introduce two application settings. The first is ID-based recommendation. So the authors combine these text embeddings with traditional ID embeddings through a fusion mechanism, as shown in the equation here. The GL function aligns the dimensions via linear projection, and the GF function is a fusion layer. This lets the model integrate both open world knowledge and collaborative signals. And for ID agnostic recommendation, in scenarios like code start, we skip the ID embeddings entirely and use only text-based reasoning as shown in the third equation. And GT function is a transformation layer that projects both sides into a shared space for similarity matching. And this architecture allows SLIM to support both traditional and ID-free recommendation tasks while keeping the recommendation process interpretable through COT rationales. The experimental results in table demonstrate that SLIM achieves state-of-the-art performance across different backbone models and datasets. And for the takeaway, SLIM enables small language models to act as effective reasoners in sequential recommendation by distilling step-by-step rationales from large language models at a fraction of the computational cost. And this is for knowledge graph. So this slide focuses on the second category of knowledge enhancement. While summary text provides unstructured descriptions, structure the knowledge graphs over a more systematic and integrable way to represent relationships among entities. And this structure is often easier to incorporate into recommender systems, especially when we need consistency and interpretability across users and items. The idea here is to utilize large language models to either generate new knowledge graphs or augment the existing ones. For example, given a prompt like, does this item have a particular attribute? The LLM can infer and output new facts or relationships that are not explicitly available in the dataset. And these outputs are structured into graphs, which are then encoded using a KG encoder and integrated into the recommendation pipeline. This allows us to incorporate high-order semantic relationships into the user or item embeddings. So we divide existing work in this direction into two categories. One is generation, where the LLM is used to construct new entity relationship, the triples, or reasoning paths from scratch. And the second one is compilation and fusion, where the LM fills in missing links or refines existing KGs to improve their usefulness in recommendation. And in practice, this structured approach helps the RS model go beyond direct interaction signals and leverage inferred relationships. Okay. And first, let's take a look at the generation. The work we introduce here is LLM-RG. Sequential recommendation aims to predict users' next interaction by modeling historical behaviors, and traditional methods, including those enhanced with knowledge graphs, often rely on static the structures and cannot generalize to unseen patterns or diverse reasoning paths. And this slide introduced the LLM-RG. It's a novel framework that leverages larger models to build personalized reasoning graphs on the fly. And instead of relying on explicit external knowledge, LLM-RG generates multi-hop reasoning chains using only user interactions and attribute information. The core idea is to let an LLM act as a dynamic reasoning engine. It first builds the candidate reasoning chains, then verifies and scores them using a self-tracking process, and finally expand them to improve coverage and robustness. LMRG consists of three modules: the trained graph reasoning, self-verification and scoring, and divergent extension. These modules work together to generate and refine user intent-specific reasoning chains, and the model fuses this with a base sequential recommender to yield the final prediction. So first, author begin with the trained graph reasoning module. For each user, the LM constructs multiple candidate chains based on their sequence and attribute, optionally referencing a knowledge store. To verify reasoning quality, trains are randomly perturbed, masking the certain items or attributes. The LLM performs abductive reasoning. Can it still explain the interaction despite missing parts? And each chain is then scored via a learned function. Only trains with high scores are retained for further use. This stage ensures interpretability and robustness before fusion with the base model. And after the verifying reasoning chains, so we now move to divergent extension. The LLM queries the graph for unexplored nodes, creating new chains that enhance diversity and completeness. If these new chains contradict previous knowledge, say if RCP yields all the text new, while the retrieved outputs is the other, the knowledge base is updated, so making the system self-improving. And finally, embeddings from the base model and original the reasoning and divergent reasoning are fused by this equation. And this factor is passed to an MLP for next item prediction. This fusion integrates explicit reasoning paths with traditional sequential patterns. So LLM-RG outperforms all the baselines across multiple datasets. For example, on the movie lens 1 million using the GPT-4, we see a 28% gain in NDCG at 10. Unlike previous models that rely on pre-built graphs, LLM-RG adaptively builds and verifies reasoning trains from scratch. It supports dynamic, user-specific reasoning and can even expand its own knowledge. And the takeaway is clear. LLM-RG makes it possible to inject rich, interpretable reasoning into recommender systems empowered entirely by LLMs without needing external knowledge bases. And in recent years, knowledge graphs have been widely used to enhance recommender systems by capturing the structured information among users, items, and entities. However, these methods face three critical limitations. First, many KGs are incomplete, with missing or sparse relationships. And second, they typically convert textual entities into IDs, losing the underlying semantic meaning. And third, most models rely on multi-layer GNNs, which suffer from noise accumulation and oversmoothing, especially for high-order relationships. And motivated by the strong semantic reasoning ability of larger models, this paper proposes the COLA KG. It's a novel approach that leverages LLMs to understand and complete KG information. COLA KG converts item and user-centered subgraphs into textual prompts, which are interpreted by LLMs to generate the semantic embeddings. These embeddings are used to construct a semantic item-item graph and are integrated into traditional recommenders using alignment and augmentation modules. So this page explains how COLA KG enables LLMs to comprehend structured KG data. Since LLMs cannot directly interpret the graphs, the model extracts a local subgraph centered around each item. These item-centered subgraphs include both first-order neighbors and randomly sampled second-order connections, represented as triples. And next, these triples are transformed into textual form. The first-order set is encoded as the flat list, and second-order relations are described using natural language. Combined with the task-specific instruction prompt, the full input is passed to an LLM. And the LLM processes this textual input and outputs a natural language comprehension, summarizing and reasoning about the item's context. A frozen sentence embedding model is then used to convert this text into a dense vector, which serves as a semantic embedding of the item. This process allows COLA KG to retain semantic meaning and mitigate knowledge sparsity by leveraging the LLM's reasoning capacity. And this page focuses on how COLA KG leverages semantic embeddings to model high-order relationships and integrate them with traditional user-item interaction models. Once semantic embeddings are obtained for each item, COLA KG constructs a semantic item-item graph. For any two items, their edge is weighted by cosine similarity. For each item, the top k most similar items form its semantic neighborhood. To integrate semantic and collaborative information, COLA KG uses adapter layers to project the embeddings into the same space as ID embeddings. The fused representations are then created by averaging. Additionally, to further enrich the item representation, the model aggregates information from semantically related items. Attention weights are computed based on embedding similarity and used to weight neighbor contributions. The final augmented representation captures both direct and semantic neighborhood information, leading to stronger and more informative embeddings for downstream recommendation. And the experiment's results, as shown in the table, clearly validate the effectiveness of Cola KG. It outperforms all baselines across 4 datasets, including both KG-based and LLM-based models. And the main takeaway of this work is that it successfully unifies structured graph knowledge and unstructured semantic information using large-end models. And this slide introduced the combination strategy, which integrates both summary text and knowledge graph representations for recommendation. While summary text provide the rich unstructured insights and knowledge graphs offer structured relationships, each has its own strengths and limitations. Some recent work proposed to combine both sources, aiming to capture the complementary information. And as shown in the diagram, LLMs are used to generate textual summaries. The summary is encoded through a text encoder, and the knowledge graph is processed via KG encoder. Both outputs are then jointly fed into the recommended system. For combination, we introduce one paper as called the REC. So educational recommendation and knowledge tracing tasks require a deep understanding of what learners know and how concepts are related. Traditional approaches often model concepts as discrete IDs, which leads to poor generalization, especially when encountering rare or unseen concepts. These methods ignore both the semantic content of the concepts and their structural relationships within a knowledge graph. To address this, the authors propose SCAR, the REC, a structure and knowledge-aware recommendation framework. SCAR-REC integrates large language model, structured concept graphs, and contrastive learning to build richer and more generalizable representations. This page presents how SCAR-REC uses language models to interpret educational concepts semantically and structurally. Each concept, such as table, is associated with a textual definition and linked to its neighbors in a concept graph. And these components are combined into a structured prompt and passed to a large language model. The prompt includes the base concept, its its predecessors, successors, and contextual instruction. The LLM processes this prompt and generates a coherent and enriched textual explanation of the concept. This LLM-generated interpretation captures both linguistic semantics and structural dependencies among concepts. It serves as a more expressive representation than traditional one-hot or ID-based encodings, enabling downstream models to understand ambitious or sparse concepts more effectively. Once SCAR-REC generates concept interpretations, it encodes them using a transformer encoder to obtain dense semantic embeddings. These embeddings are then aligned through a graph-based contrastive learning objective. And the concept graph is constructed based on the prerequisite, the relationships between concepts. For each concept, authors define positive pairs as its direct neighbors and negative pairs as non-neighbors. The model is trained to bring embeddings of positive pairs closer while pushing negative pairs apart, thus encoding both semantic and structured signals. And the resulting embeddings are used in 2 downstream tasks. First, a transformer-based recommendation model processes sequences of concept embeddings and predicts the next concept or answer. And second, for knowledge tracing, the model estimates a learner's mastery of each concept using the enriched embeddings, and this dual application demonstrates the generalization of SCAR-REC representations across both recommendation and knowledge modeling. And the results in table clearly show that the SCAR-REC sets a new state of the art on three widely used educational datasets. And in summary, ScotRec demonstrated that incorporating both knowledge structure and semantics is essential for building effective educational recommendation and knowledge tracing systems. And here we give a summary of knowledge enhancement section. For a summary text, this work used LLM to generate natural language summaries that describe either user preferences or item characteristics. These summaries serve as additional semantic features for traditional recommender systems, improving both reasoning and personalization. For knowledge graph, the idea here is to utilize LLMs to either generate new knowledge graphs or augment the existing ones. For combination, which integrates both summary text and knowledge graph representations for recommendation, while summary text provides rich, unstructured insights, and knowledge graphs offer structured relationships. Each has its own strengths and limitations. Combined, both sources can capture complementary information. Thank you.
LLM can also be used as interaction enhancement. We basically divide the category in two aspects. The text-based aspects, as shown in Figure A. Text-based methods first conclude the candidate set and then utilize LLM to conduct the possible next interactive item to achieve the augmentation. And for the score-based method, we can see it in the Figure B. The score-based methods utilize LLM to rank the importance of each item and then leverage this ranking score to do the augmentation. So in this section, we present several insightful papers that leverage the power of LLM as user-item interaction enhancement. We will first introduce 4 representative text-based works and then present 3 awesome score-based works. Okay, for the first one, we present LLM Rec. And this work recognizes the limitation of regarding LLM as a data augmenter and summarizes them as 2 problems. Problem 1, incomplete input information, which means it's hard to enable LLMs to reason over full user-item interaction patterns due to the limited input token. And problem 2 is low quality of regenerated data, which means LLM generator often introduce low quality content that may compromise the results because of the noise and hallucination. So specifically, to address the first problem, they also designed 2 individual modules from a natural language perspective. For the implicit feedback augmenter, since LLM's limited length of input token often introduce the incomplete interaction information, they also first construct an item candidate pool by leveraging a basic recommendation model, and then randomly select the historical interactive items with side information to feed them into LLM for data generation. And moreover, they also design a user profiling and item attribute enhancing module to summarize user interactions and unify the item attributes, further alleviating the problem of limited input token. And for problem 2, they also propose the other 2 modules. In the augmented implicit feedback noise pruning modules, they also leverage the ascending sort mechanism with the BPR loss to filter values and select the top N scores. And for other modules, they also did first randomly mask the features of selected subset of the node, and then replace them with LLM-generated feature vectors. And after that, they leveraged the feature restoration loss to compare the masked matrix with the original one to further enhance the feature encoded. And for the experimental results, LLM Rec achieves remarkable results on the 2 public datasets and beats all the compared baseline with significant improvement. And that is the first article. For the second one, we introduced Llama Rec. And this paper identified the shortcomings of conventional methods known as data sparsity and long tail problem, and also the shortcomings of LLM-based methods known as collaborative information loss. And it also raised 3 research questions. And question 1, how to leverage LLM's reasoning ability in conventional methods. And question 2, how to introduce collaborative information in LLM-based methods. And the last question is how to aggregate the LLM-based method and conventional methods properly. So here is an overview of the framework. which allows the conventional and LLM-based argumentation to mutually augment each other and adaptively aggregate results for different kinds of recommendation. And then we will detail how LlamaRag answers the mentioned research questions. For the first questions, they also propose the data augmentation. For the direct recommendation task, they prompt the LLM to rank each item pair based on the user's likely preference and rewrite the corresponding BPR loss like this. And then, for the sequential recommendation, they leverage LLM to predict the user preferred items in the uninteracted list, and then inserting them in the interaction sequence. And when it comes to the rating prediction task, the LLM is prompted to do in-context learning to provide side information of item features. And to answer the second questions, they also designed two prompt augmentation strategies. The first one utilized the information from similar users. Specifically, it leveraged cosine similarity to recognize similar users and regarding the interactive items of these users as collaborative information to enrich the prompt for LLM instruction tuning. And the second one is quite simple. It just combined the prediction results from conventional methods within the prompt to do the augmentation. And lastly, to answer the question 3, LlamaRag introduced adaptive aggregation to aggregate the outputs of different models by leveraging this predefined long-tail coefficient, which quantify where the user is located in the tail of distribution as follows. It can calculate the utility score for no matter rating prediction task or the top K recommendation task to adaptively aggregate the advantage of conventional model and LLM-based model while relatively alleviate their shortcomings. And experimental results present that LlamaRag shows optimal performance no matter the backbone is direct recommendation models or sequential recommendation models or rating prediction models, validating the effectiveness of design framework. And for the next article, we present LLM HD. And this paper identifies the challenges that hinder the direct application of LLM in denoise recommendation and conclude them as 3 challenges. Challenge 1, high cost of LLM summarization. And challenge 2 is identifying of hard sample and noise, which is shown in the left figure. Hard samples and noise samples tend to present similar patterns in both prediction score and loss values. However, conventional methods are struggling to distinguish this difference, leading to the suboptimal performance. And challenge 3, biased user preference summarization. And here's an overview of the framework. And next, we will detail the role of different modules and clarify how they solve the corresponding challenges. For challenge 1, LLM HD introduced the variance-based sample pruning. Following the observation of previous work, hard samples present relatively higher prediction score variance compared to noise samples. LLM HD calculate and sort the prediction score of the positive and negative items as follows. So the hard samples can then be defined as this, which can provide to feed all identified noise samples to the LLM for scoring, significantly reduce the computation cost of LLM. And for the challenge 2, LLM HD introduced a novel sample scoring modules. Specifically, they also designed 2 paradigms, pairwise and pointwise. For the pairwise, they set different thresholds to control the hardness of samples, and to avoid the problem that harder samples at the early training stage might hurt the generalization ability. They also smoothly changing each threshold during each training iteration. And considering the user preference for the positive item does not significantly surpass the negative one, the authors also propose a pointwise sample scoring. It utilizes indicator functions to calculate the difference of 2 thresholds and then doing the selection procedure like this. And lastly, to adjust the challenge 3, LLM HD introduced the iterative preference updating module to alleviate the side effects that false positive and false negative item brings. Specifically, they also refine the user preference iteratively by excluding dislikes and incorporating likes, and then precising the variance score of each user item pairs in positive and negative groups to select the confident items. And at last, leveraging these content items, LMHD can refine the original preference based on the identified false positive and false negative to construct the unbiased user preference. And in the comprehensive experiment, LMHD shows remarkable recommendation ability under 4 different recommendation backbones in 3 public datasets evaluated by 4 metrics, validating the effectiveness of design structure. And okay, for the last work under the text-based category, we present sample LLM. In this work, they also find the difficulty in applying LLM to tabular data synthesis and conclude them as 2 severe problems. Problem 1, inconsistent distribution and diversity. As shown in the left figure, these challenges arise from a distribution mismatch between LLM's inherent knowledge and target dataset. And problem 2, distribution difference caused by LLM. And this is because of the inherent difference caused by LLM's input and output processing, which resulting a distribution gap and differentiated feature interaction frequency. So the figure below is an overview of the whole framework, and next we will detail the role of different modules in different stages to clarify how they solve the corresponding problems. And to adjust the problem 1, in the first stage, the design instruction and sample exemplar from the original dataset are selected to serve as an input for LLM, producing the initial synthetic tabular data. And beginning with the example selections, simple LLM leverage k-means methods, which can ensure that each group of exemplars contains samples from diverse regions of original dataset distribution by only using these clusters for LLM feature learning. The whole approach can then be formalized as follows. And to adjust P2, sample LLM performs a feature attribution-based importance sampling operation. Since it is challenging to assume each feature field is independent and impractical, they propose a new semi-independency assumption. Feature fields containing significant interactions are non-independent, while others are independent, to satisfy this situation. However, it is still challenging to identify which interaction is significant. So they designed the feature interaction extractions module. And specifically, they quantify the importance of each feature to the output by approximating model performance degradations after ablating this feature with the first-order Taylor approximation, and extend the first-order Taylor expansions to the second order to capture the importance of feature I to the importance of feature J. So therefore, the sum of absolute value of interactions can highlight the significant features interactions in the whole dataset and can be used for further data alignment refinement for the non-independent and independent feature groups. And then, since each tabular data contains not only a set of features, but also a label, those are also designed to chain a task-specific model to acquire the labels. And at last, leveraging these well-chained discrimination models and acquired feature groups, the importance words of samples can then be formalized as follows. So the experimental results have shown that a sample LLM achieves remarkable results on 5 public datasets, validating the effectiveness of proposed methods. They also first tested the utility of the synthetic data by comparing the prediction performance of different methods after injecting synthetic data into the original data. And they also validated the utility by supplanting the real data with synthetic data in training a predictive model. And next, we will introduce 3 remarkable work under the score-based category. For the first one, we present LLM-ins. And this work identifies the limitation of current methods as 2 challenges. Challenge 1, distribution gap, which means the generated embedding are created from content features, while the behavior embedding are changed from user item interactions, leading to the distribution gap in the figure A and the performance gap in the figure B between the cold items and warm items. And challenge 2 is LLM's inadaptability. So here's an overview of the LLM-ins framework. The LLM simulator is designed for generating possible user set for the code items. And the hierarchical interaction simulator, which is the main procedure, is designed for mimicking potential user interactions for each code items and then transfer them to warm items. And the embedding updating is designed for adaptively merging the interaction of cold items and warm items. And we will then detail the procedure of the hierarchical interaction simulator, which is the main procedure. And okay, for the hierarchical interaction simulator, It contains two parts, the embedding-based filtering and the prompt-based refining. The purpose of the embedding-based filtering is to ensure the candidate selections align closely with the real-world scenario. And specifically, it processes information on both the semantic and collaborative side. To process the semantic information, the author constructs a llama subtower to obtain the user and item representation and leverage the BCE laws below to train the substructures. And to process the collaborative information, the author constructs another collaborative subtower. Specifically, it contains three kinds of laws to leverage the collaborative information. The main BPR loss is to narrow the gap between embeddings of code items and the well-trained embedding of warm items. And the DIS loss is proposed to enhance the consistency between the corresponding embeddings on the collaborative side and non-collaborative side, while the IDE loss is to achieve consistency on the embedding distance side. Leveraging these three laws, the model can enable the site without collaborative information to learn information related to the recommendation task. And after obtaining this embedding from Llama Tower and Collaborative Tower, LLM aims leverage the prompt-based refining to further refine the generated interactions. And it first concatenates the two embeddings together to get the overall representation, and then utilize the inner product to avoid them interfere each other. Then utilize the well-constructed instructions to prompt the LLM to filter the low-quality interactions. The experimental results shows that LLM achieves optimal results under 3 backbone MF, NGCF, and LightGCN, and present remarkable performance in comparison with other LLM-based recommendation models. And next, we will introduce another score-based interaction enhancement methods, LLM for DSR. And this work also aims at denoising sequential recommendation and identify two severe challenges when directly applying LLM to denoising SRS. And challenge 1, inability of LLM, which means direct application of preaching LLM might not be competent for the denoising task. Figure in the left illustrates an example where LLMs typically misidentify all items in the sequence as noise. And challenge 2 is the hallucination of LLM. So here's an overview of LLM for DSR, featuring with self-supervised fine-tuning methods and the uncertainty estimation mechanism to fully explore the capability of LLMs. So specifically, to adjust C1, LLM for DSR construct a new dataset and leverage supervised fine-tuning to empower LLMs with denoising ability by using a find and replace task. By prompting LLM using left instruction example, the authors construct a new binary prediction tag dataset and formalize the training objective as follows. However, there's still one limitation that hinders current LLM-based denoiser, which means they can only adjust one single noise items per sequence. And they raise the L1 inadaptability for multi-noise scenario. So to address this problem, the author proposed the uncertainty estimation model to gauge the model's confidence in its response. Regarding LLM's provided probability after text noise items as LLM's confidence in identifying the noise. The problem can then be simplified as follows to obtain the probability values of all noise items in the sequence. And this probability serves as an indicator of LLM's confidence in identifying the noise as noise. So, moreover, the experimental results shown in the left further confirm the reliability of the probability provided by LLM. The experimental results shows that LLM for DSR achieves optimal results on 3 low public datasets. Moreover, to highlight the denoising ability of LLM for DSR, they also conduct experiments on the same 3 public datasets while randomly adding some extra noise. From the result table, it is notable to see that LLM for DSR maintain the performance, while other methods show a significant decrease. Okay, for the last paper under score-based interaction enhancement, we introduce EIMF. And this work identifies the problems when leveraging the semantic information to model user behavior information and categorize them as two problems. Problem 1, demand conflict, and problem 2, misunderstanding of users' real interests. So here's an overview of the framework, featuring with an implicit behavior interest model, an explicit semantic interest model, and a joint learning modules. And next, we will detail the role of each component and clarify the methods behind the motivations. To adjust the P1, ELMF introduced the explicit behavior interest to fully explore LLM's capability while reducing the inference cost. For the first step, EMF divides users into groups and utilize LLM as summarizer to reduce the inference cost. And then, for the interest embedding, EMF queries the semantic interest embedding by utilizing the target data as a key, which can be used for further alignment and semantic prediction. And to adjust P2, EMF then combines the implicit behavior interest with the explicit semantic interest by joint learning three kinds of tasks. Firstly, EMF obtains the implicit behavior interest by a normal SR model, and then using similar target-aware attention network to acquire a behavior embedding to construct a loss. And when it comes to the joint learning of three tasks, for the first task, they calculate the score between the user semantic interest and item text. And for the next one is the modern alignment task. EMF builds the constructive loss to align the semantic embedding and behavior embedding like this. And after that, EMF constructs the main recommendation task, which multiplies user behavior interest representation and the item representation to calculate the probability and construct the following red loss. And finally, the whole loss can then be formalized as the weight sum of the three laws mentioned before. The experimental result shows that EMF achieves remarkable results on three public datasets, two large and one small, presenting that EMF superiority. And moreover, the experimental performing on different backbones shows a significant improvement, further validating the effectiveness of proposed modules in EMF. So here we give a conclusion of the frameworks in interaction enhancement for LLM enhanced sequential recommendation. The text-based, this kind of methods leverage LLMs to give out the name of procedure interacted item in the user item interactions as the argumentation. And the score-based methods utilize LLM to derive the logics of possible interactions and generate the argumented item by ranking.
Hello everyone, I'm Yejing Wang and I will conclude today's tutorial. To begin with, let me first summarize today's tutorial. From our previous sessions, we can categorize existing enhancements for recommendations into three categories. The first is knowledge enhancement, and the second is interaction enhancement, and the last one is model enhancement. For the knowledge enhancement methods, they usually utilize the word knowledge and the strong reasoning ability of LLMs. This sort of solution typically enhances traditional recommender systems with explicit semantics. And the second category, interaction enhancements, relies on the generation ability of large language models, whereas augment the training data with rather implicit or explicit semantics. And the last one is the model enhancement. This kind of method uses the strong representation ability of large language models to enhance recommendations with implicit semantics. And an important motivation for designing LLM ERS methods is their outstanding efficiency compared with LLMS recommender methods, as the enhancements can be pre-computed offline instead of conducting the real-time inference for online serving. However, the offline efficiency is still an important topic for this kind of method. We will next compare the offline efficiency of different categories. And for the typical process of knowledge enhancement involves knowledge encoding by large language models and further conversion to representations with small language models, such as BERT. And this process requires the dual encoding of large and small language models, which may require large storage and is hard or inefficient to realize daily updates. And the second one, the interaction enhancements can be rather inefficient as they do not change the training and inference procedures of recommendation models except for providing augmented interaction data. This implies that they are highly scalable to big data scenarios. And the last one, the model enhancement methods, they typically relies on the LLM representations. They may encounter compute encoding and storage issues to prepare, update, and storage the item representations from large language models. However, they are still more efficient than the first category, that knowledge enhancement method, as they do not require further conversion of small language models, right? And they also can avoid the lengthy output problem for knowledge. And to analyze the trend of LMEIS researches, we visualize the representative literatures on how they use LLM semantics in the vertical direction along this y-axis and the large language model types, whether they use the closed source LLM or open source LLM along this horizontal direction, this x-axis. And we also represent the type of enhancements in the different shape and denotes how whether they are fine-tuned with different colors. And from this figure, we can find that for the semantics, we can find that the researchers initially explore the explicit semantics around here. You can find that the initial works like Wang's and KI is proposed in 2023, right? And nowadays, researchers focus on design implicit semantics-based method, especially the model enhancement solutions in the shape of stars. You can find that here almost all the method is in the shape of star, right? And for the LLM types, open source large language models on the right of this figure is more welcome because they can be fine-tuned for specific recommendation tasks. And they are more easy to easier to be deployed and are highly adaptable compared with closed source LLM like GPT. And next, we want to share some insights on future direction for enhanced recommender system. And first is that large language models can be extended to diverse recommendation tasks. Existing works have focused on revolutionizing several basic recommendation tasks like collaborative filtering and sequential recommendation. However, they have proven the effectiveness of bringing the semantics of large language models to traditional recommender systems, and this indicates that it is also promising to replicate their success in some other recommendation tasks, such as multitask and cross-domain recommendations, right? And in addition, current enhanced recommender systems rely solely on textual input. How to extend the current framework to other input compositions, such as multimodal or text-free systems, might be challenging. For multimodal input, merely replacing large language models with multimodal large language models might not be enough. Merely replacing LLMs with MLMs might not be. For example, for e-commerce platforms, some products may rely on textual description for fine-grained information, like suitable font versions for font cases products. And while for the clothing products, we distinguish different ones mainly based on the visual patterns, right? So a unified representation from multimodal large language model cannot support adaptive representation. How to build a multi-model LLM enhanced recommender system is still an open problem. As for text-free scenarios, it may be associated with tabular data comprehension, especially when most features are continuous values. And the last one is user-centric enhancement. Current based user enhancement typically relies on the concatenation of item descriptions in prompt or the integration of enhanced item representations. This method can lead to the lengthy prompt and behavior-unaware integration. As a result, user-centric enhancement might be a promising direction, which may include item-free user enhancement and behavior-aware item integration. Also, there is still some open problem for LLM frameworks. First, compared with LMS recommender system solutions, LLM is very efficient. However, for some practical scenarios, it may contain billions of items. It requires lots of computational and storage resources to encode and store item representations with large language models, which is still impractical compared with traditional recommender systems. In these scenarios, return on investment might be limited to developing LMEIS. As a result, it is still important to develop more scalable LMEIS frameworks. And secondly, explainability is an important aspect of trustworthy recommender systems. LMS is a promising solution to enhance this for recommender systems, but current LMEIS frameworks do not address this problem. It might be valuable to explore how to generate explanations while enhancing recommender systems with large language models. And lastly, it is hard to evaluate and compare the effectiveness of LMEIS frameworks. Current conclusions are based on the integration of LM enhancements into traditional recommender system. The effect of solely LM enhancement cannot be measured. Maybe some specific benchmarks and metrics can tackle this problem. And that's all for today's tutorial. You are welcome to join our chat group in WeChat or visit our lab website, and you can get our tutorial slides in with this QR code. And also, you are welcome to visit to read some of relating service provided by us. And that's all.